All right.
And we're happy to have Greta Panova here for the very last IPAC talk of this summer. She's speaking on all Kronecker coefficients are reduced Kronecker coefficients.
Thank you so much. Thank you so much for the invitation and the interest in that paper. So as the title of the seminar suggests, so this talk is going to be about a paper, which is this thing here on the archive with the same name, which we wrote with Christian Ickenmeyer a few months ago. So, but before I tell you about the results of the paper, I need to give you some introduction about the problems and the objects that we're studying and where this whole thing is coming from. So, crash course in algebraic combinatorics, which probably you don't need. So we have integer partitions, which we denote by the Greek letters lambda, where we draw as Young diagrams like this here. Then we have, of course, standard Young tableau. I'm not going to really use that in the talk, but just a connection with everything else you probably know. This is when we write the integers from 1 up to n in the boxes so that they're strictly increasing along rows and down columns. And where do standard Young tableau really come from? They come from the representation theory of the symmetric group. So they are irreducible representations of the symmetric group are indexed by the partition lambda of n and are called the Specht modules. And the dimension of each Specht module is actually equal to the number of standard Young tableau of this particular shape. And they have some, the characters of the representations are integer values, and can be computed by the Murnaghan-Nakayama rule. And as another result we recently have, that the characters are pretty complicated in strictly computational complexity way. All right. So the irreducible representations of the general linear group are also indexed by partitions. This time the length of the partition, so the number of non-zero parts, is bounded by the size of the matrices in the general linear group. These are the Weil modules, and the characters for these representations are actually our favorite Schur function. So I'm sure everybody knows about Schur here, so I'm not going to spend time explaining, and I'm actually going to use them quite a bit. But just to put things in perspective, the Schur functions can be combinatorially considered as generating functions for semi-standard Young tableau. So these are what's called semi-standard Young tableau, abbreviated SSYT. And the integers we put in are weakly increasing along rows, strictly increasing down columns, and the monomials correspond to exactly what's written inside. But there are other formulas for the Schur functions, which I'm going to use later in actually to prove the results. Okay, so where do we go from here? So here, in some sense, we do understand the irreducible representations. So the next thing we can do is we can take tensor products. So here is something you're probably all very familiar with, Littlewood-Richardson coefficients, which are the multiplicities of irreducible GLN representation when you take tensor product of two others. So this is representation theoretic definition. From it, what we get is that these guys here are non-negative integers because they are multiplicities. But we can also study them with characters. So in this case, the Schur functions, and they are basically the structure constants for the ring of symmetric functions as indexed by the Schur functions. This is what shows up. And they can be computed, as we all know, by the beautiful little Richardson rule, which is telling you, not very important exactly what it says, but that this number is equal to the number of skew semi-standard Young tableau of shape, let's say nu minus mu, and type lambda, type meaning that the number of ones is equal to lambda 1, the number of twos is equal to lambda 2, and so on. There is another condition that the reading word should be a ballot sequence, so it's not all semi-standard Young tableau, it's just actually a very small portion of them. And so this rule motivates a lot of questions and research in algebraic combinatorics. In particular, we next can define the analogous quantities, the analogous multiplicities for the symmetric group representation. So if we take tensor product of two Specht modules, so these are symmetric group representations, we can decompose it. It's a representation of the same symmetric group. We can decompose it into irreducibles as mu with some multiplicity, which by definition, again, algebraic representation, theoretic definition, these guys here are going to be non-negative integers. These are the Kronecker coefficients. Using Schur-Weil duality, we can study them with Schur functions, where here x times y means that we take all pairwise products, x1 times y1, so x1 times y1, x1 times y2, and so on and so forth. And now this is symmetric function in the x variables and the y variables, so we can decompose it in these bases separately, and turns out that the coefficients we get are the Kronecker coefficients, but just from this definition already, we don't really see why this is non-negative integer. There is another definition we can use for the Kronecker coefficients, which come from the characters. So these are the characters of the symmetric group evaluated at permutations. As I said, these are integers, but they are positive and negative. Never mind that we're also averaging out over one over n factorial. So this thing is not clear. It's an integer, and non-negative integer even less. And so these questions, so these definitions are all are motivating the question: how do we first compute these Kronecker coefficients, and in particular, can we see in a more combinatorial way that they are non-negative integers like we have for the little Richardson coefficients? And in particular, Murnaghan, when he started working with Kronecker coefficients, so they were defined by him in 1938, he observed that the little Richardson coefficients are equal to Kronecker coefficients where of these partitions. So we take the partitions lambda, mu, and nu for the little Richardson, and we add to each one of them a long first row so that the total size is the same. Is this some big integer n? And if when the sizes of lambda is equal to the size of mu plus nu, this actually happens to be a little Richardson coefficient. So they are special cases of the Kroneckers, and from then on, what other properties of little Richardson would carry over to the Kroneckers, which are, as we see, more general. So this is the main question that people ask. So Murnaghan was interested in computing them. He didn't really, combinatorics back then was not such a big thing to ask for a combinatorial interpretation, but later on, so Lescaut and Garcia Remmel studied them, and Stanley listed it as problem number 10 in his open problems in algebraic combinatorics from year 2000, that we want to find the combinatorial interpretation for these numbers, or set of some discrete, so nice, relatively nice combinatorial objects indexed by lambda, mu, and nu, such that the Kronecker coefficient is equal to that, to the number of such objects. Okay, so what do we know? Not much about the Kronecker coefficient. So here are some results of various special cases. Maybe the most general case is due to John Blasiak, where one of the partitions is a hook and the other two are arbitrary. But so there are various other special cases that have shown up in various works. And still, from bird's eye view, these are measure zero number of cases that we actually know. So very small set. There are other questions you can still ask. So combinatorial formula is really maybe the end game, but before that we can ask about positivity. So when are these coefficients positive? And in particular, there are a bunch of conjectures saying that, so the tensor square conjecture says that the Kroneckers are positive. There exists some partition lambda for every n, such that G lambda lambda mu is strictly bigger than 0 for all partitions mu of n. And Saxel actually conjectured that the staircase partition, which is this thing, looks like a staircase if you draw it, this would do the job for n triangular number. And there has been some work and along on this, but as I will explain in a moment, the question in general is actually hard, so computational complexity hard. And another place where the Kronecker coefficients come in and have spurred some research from that direction is geometric complexity theory, which is concerned with distinguishing algebraic computational complexity classes like VP versus VMP, going through some algebraic geometry and representation theory, and in the end it boils down to comparing some multiplicities which are closely related to the Kronecker coefficients and the Pletizan coefficients that I'm not going to talk about today, but we need to understand them from that perspective, and this and from this research motivated the study of this rectangular Kronecker coefficient. So this is the partition where it has, where the Young diagram looks like a rectangle, n by d rectangle. And
before you go,
yeah,
Greta, in the last one, you left it as saying for the rectangular case, mu, certain mu's.
yes.
Are there something describable like the triangular in the earlier ones? The mu?
So for when we say certain mu's, what we mean is that actually I mean some very specific mu's, but I just didn't want to describe what they are.
Okay.
So I unfortunately, in order to actually write this down, I will need to introduce some more parameters and explain what the restrictions on n and d are with respect to these parameters. But briefly, these would be mu's which have relatively long first row and relatively little short height.
Mm-hmm.
So this is big compared to what's going on here.
I see. Thank you. That's good.
Yeah. So I think in one of the next slides I will briefly show this fact again. and you'll see what kind of parameters are involved in that. Yeah, it's not there. So the reason for this is that we cared about these quantities from geometric complexity theory. That's why it looks complicated. On the other hand, I mean, I'm sure that one can prove various other results of this kind in more generality. And in fact, my student Chen Zhao is going to put on the archive some work along those lines for positivity of Kronecker coefficient. And so, as I said, I mentioned computational complexity a few times. So these problems are related to computational complexity theory in two ways. So one way is computational complexity theory can formalize what's so difficult about these Kronecker coefficients and what kind of formulas can we expect for them. And on the other hand, as I just mentioned, the geometric complexity theory is using these coefficients in order to very broadly speaking, to try to distinguish computational complexity classes. So this is the algebraic analog of P not equal to NP, maybe P not equal to VNP. And there is another area of research separate, which we're not going to discuss. Okay, so what else can we ask? So we don't really have combinatorial interpretation. We don't really have a lot of positivity results. We can ask about asymptotics. How do these coefficients grow? And this is another area of research which has recently picked up. And I will mention some of these results in a moment. And this is another natural question. Of course, this is related, also motivated a little bit by this geometric complexity theory, because as I said, we need to somehow compare coefficients and we need to understand how large they are. Okay, so this is general introduction on Kronecker coefficients, which we have not even mentioned the reduced Kronecker coefficient. So let me do this now. Any questions before I move on? All right. So here are the reduced Kronecker coefficients. So they are stable limits of the normal Kronecker coefficients. And in that sense, the reduced Kronecker coefficients are already equal to certain Kronecker coefficients by definition. So how do we define them? We take three partitions, alpha, beta, and gamma, and this time they don't need to have the same size. And we make these augmented partitions where we add in a long first row. And so now the new partition actually has size equal to n. And then we take the Kronecker coefficient of these three partitions. Now they are of the same size. And it turns out, this is a theorem not obvious, that when n is going to infinity, these integers here stabilize. And this is what the reduced Kronecker coefficient is. So the reduced one is G with a bar on top. And in particular, Morne-Gans result is telling us that when alpha is equal to the size of alpha is equal to the size of beta plus the size of gamma, then these guys are actually our favorite Littlewood-Richardson coefficients. And then Kirillov called these reduced Kronecker coefficients the extended Littlewood-Richardson coefficients, because, well, obviously they generalize the Littlewood-Richardson coefficients and kind of look like them in some sense, in some broad speaking sense. And he stated it as a problem almost 20 years ago to find a combinatorial interpretation for the reduced Kronecker coefficient. So of course, if we had a combinatorial interpretation for the Kronecker, by this formula that would be done. But maybe, so this is something special, maybe these guys are going to be easier, and maybe we can find the combinatorial interpretation for them more easily than for the original or ordinary Kronecker coefficients. And so here, so there was work on this, on the reduced Kronecker coefficients of their own. On their own, there were some combinatorial interpretations. Of course, some of them would follow from the general Kronecker coefficients interpretation that we have, but some are special because, as we said, so when we have a long first row, some borderline cases disappear. So they have been studied from various sides. They show up as structure constants, as Mike would probably be able to tell us more, and maybe you actually already spoke at IPAC about this. So the reduced Kronecker coefficients have a life on their own, and there are some interesting proper relationships between them. So I can show you one of the nice formulas from this paper, that the reduced Kronecker coefficient can be expressed as some, so this is a positive sum of multi-Littlewood-Richardson and Kronecker coefficients for smaller partitions. And actually, so also there is another formula, but it has signs which expresses Kronecker coefficients in terms of some sign sum from the reduced Kronecker coefficients. So, so what happened, kind of motivated maybe by this relationship here, there were a bunch of conjectures for the reduced Kronecker coefficients other than the general question. So, as you probably know, Littlewood-Richardson coefficients obey saturation property, meaning that if we scale the partitions by some integer n and the Littlewood-Richardson coefficient happens to be positive, then the original Littlewood-Richardson coefficient is also positive, and the other direction is kind of obvious. So one direction in this equivalence is easy, but the other is very much non-trivial. And this prompted Kirillov and Klyachko independently to conjecture that the reduced Kronecker coefficients also satisfy the saturation property. And again, so there is a semi-group property which is telling you that in one direction it does hold. So if this thing is positive, then the scaled partitions would also be positive. So this direction is easy, and it's true. So the Kronecker coefficients didn't satisfy this, but unfortunately also the reduced Kronecker coefficients did not satisfy this. And in particular, we can do a very explicit example of 3 partitions for which the reduced Kronecker coefficient is 0, but the scaled one is actually not. And in fact, there are many, there are families of counterexamples we can build along these lines. And so this is this result from this geometric complexity theory paper that this is what the partitions are gonna look like. So here are these parameters, Theodros, that you that I mentioned. So we have some funny looking bounds, and basically for any partition gamma, if we take some large enough A and B, then this is going to basically be positive. That's that's what this result is saying. And this is how we create all these families of counterexamples. So what else about the reduced Kroneckers? We can ask about their asymptotics. So Stanley found that the very, very maximal Kronecker coefficient is about the order of square root of n factorial. And we found that these lambdas will have to, these partitions will have to follow the what's called the Cauchy-Kellerhoff-Logan-Shep shape. And then we ask the same question about the reduced Kronecker coefficients, and the reduced Kronecker coefficients are also pretty big. So along those lines of this, the order, so square root of n factorial. So they, in this sense, they behave very similar to the Kronecker coefficients. And of course, so the computation, from computational complexity point of view, we also ask the questions, how easy, in what computational complexity classes is computing them or deciding their positivity. And this is a whole another set of talks of what this computational complexity classes are and why this this is relevant. But just to say this in the background, so deciding Kronecker positivity is NP hard. So there couldn't be a very simple rule for that. Computing them is sharply hard. Again, so there wouldn't be something nice and easy for that. And one can ask the same question for the reduced Kronecker coefficients. And we show that this is going to be sharply hard. But we couldn't quite say that computing them is going to be, deciding their positivity is still going to be NP hard. And this is the question that was left over. And that prompted us to do what we did next. Okay. Oh, any questions so far? So this is still on the background side. Okay, so it turns out that there is a reason we have all the similarities between Kronecker, the ordinary Kronecker and the reduced Kronecker coefficients in terms of their behavior. And this is this formula. So for every 3 partitions, we take the Kronecker coefficient, and we can make another 3 partitions such that this Kronecker coefficient is equal to the reduced Kronecker coefficient here. And so visually this looks like this. So this is these are our lambda, mu, and nu. And what we do is, so this is our lambda, we are going to add a rectangle to lambda. This is our mu, we're gonna add a rectangle to mu, and this is our nu, and we're gonna add the rectangles to nu, but on top. So these are the same rectangles we're adding. And it turns out that the Kronecker coefficient for lambda mu nu is equal to the reduced Kronecker for these 3 guys. All right. So of course, what is the reduced Kronecker is itself a Kronecker coefficient. So reduced Kroneckers are Kroneckers already. So now it's basically the equivalence is 2A. So this, let me see if I can draw it. So this is basically saying that so the reduced Kronecker is the normal Kronecker when we add a very long first row to our partition. So this is what this identity is really saying.
Greta, can you prove this combinatorially?
Yes, that's what I'm gonna do now.
Okay.
I mean, okay, so combinatorially using sure functions. So because we still don't have a combinatorial rule for this for any of this, so we cannot use that. So it's not exactly combinatorial, but it's going to use. I mean, in fact, there are 3 different proofs of this fact. 2 of them are using sure functions, and 1 is using representation theory. So I'll explain how this works now. So before I go into the proofs, are there any questions about the statement? So in particular, this identity explains everything else I told you before. So it first of all, it tells us immediately that deciding positivity of the reduced Kronecker is also going to be NP hard, because the Kroneckers are NP hard. Computing them is also going to be sharp P hard. This also explains why the saturation fails, the asymptotic bounds, and so on and so forth. And so one can interpret this result in the positive and in the negative. So of course the work done on reduced Kronecker coefficients now applies directly to Kronecker coefficients, which is good. On the other hand, Kronecker coefficients, being so complicated, are basically telling us that the reduced Kronecker coefficients are also going to be complicated. So okay, so all right, so how do we prove this? And so I'm going to show you first with using symmetric functions and combinatorics.
Greta?
Yeah.
In your theorem here, given lambda, mu, and nu of the same partition of n, and on the right-hand side, you constructed some partitions so that the reduced one will be equal to the original one. So my question is, the choice you made on the right-hand side of the partitions, is that canonical? Or can you choose another partition to equal this?
For these ones? It's not, I think it's not canonical. You can, but it's probably it's kind of minimal in some sense, but we are beyond listing all possible identities we can have here. So you will see how the proof works, and basically you can make these partitions bigger if you want. It's still going to, like, you can make these rectangles kind of bigger or bigger in this direction. It's still going to, you're still gonna have identity like that.
I see. Okay.
For example, but yeah, so of course the main question is how so once you have this formula, it's not so hard to prove it, as you will see in a moment. So how did we come up with this to begin with, and how is going to be answered also by the proof that I'm going to show. So
I just had a quick question.
Yeah.
So on the left, it's completely symmetric in the 3 partitions, but on the right it isn't?
Yeah.
Okay, so is that?
Yeah, so we have to break the symmetry.
Okay,
We can make it kind of more symmetric, but not entirely. And you will see now in the proof why this is the case. So there is a little bit of a symmetry breaking going on.
thank you.
Yeah. Okay, so first, maybe this is kind of gonna answer why the symmetry disappeared. So first identity, which is so from representation theory from the general linear group side, it's quite easy to prove, but also from Schur function. If we have 3 partitions, we take G lambda mu nu, and if we add rectangle, another rectangle, and a really long first row, first column to these partitions, we have identity of these Kronecker coefficients. So why is this? So here I'm gonna prove this using Schur functions because we are combinatorialists and that's what we like. So let's call this new head this partition over here. This is our new head. And so if you remember a while ago, I showed this formula. So the Kronecker coefficient is basically the multiplicity which shows up when you expand this platistic evaluation of Schur function at the pairs of at the pairwise products of variables from x and y in terms of these two Schur functions. So now we restrict ourselves to only finite number of variables. This identity still holds, right? So they can just plug in the other ones being 0. And now we evaluate this now polynomial at this point. So what's gonna happen is that the number of variables, the total number of distinct variables, is L times M. And what is this Young diagram is the height is also L times M. So if you are looking at some semi-standard Young tableau of this shape, you are forced in this column to put all the integers or whatever, all the entries you can choose to put in, they all have to be here exactly, each appearing exactly once, because this is strictly increasing. And so what are our variables are really like 1, 1, so they are pairs of entries from the x and y. So we already have this part here is fixed, and this is contributing all variables that appear here. So for all ij, the variable is xi times yj, which we can rewrite in this form. And then the rest, what's the rest? Well, the rest, this here is the shape mu, and the shape mu. Now we don't have any restrictions on this because we put the minimal entries in our first column, so this can be any semi-standard Young tableau and of shape mu, so we just evaluate the Schur function as nu at this pairwise product. And if we do this by the rules that we know, this thing is equal to this by definition, sort of. The Kronecker coefficient, rho and nu are partitions of M. And now we also have to evaluate what's happening with the other partitions. So if we this is L, this is mu, this is M. So when we evaluate the Schur function at y1 up to ym, again, because the height is exactly m and we have m variables, we are forced to have here one specific Young tableau. And then all these variables, this portion comes out, this is fixed, the rest is just any other semi-standard Young tableau of shape mu. So it gives us the Schur function, and the same thing for this lambda and L. This time this is reversed, we get this Schur function. And now basically everything here, this and these things cancel, and we are looking at an identity. So what we are left with remains the Kronecker coefficients for this lambda and mu. Okay, so this is just an evaluation, basically comes from the evaluation of the Schur functions. The next thing we can do is we can compose this lemma twice. And this is what I'm gonna do. So we start with lambda, mu, and nu. And so there is one property of Kronecker coefficients is that we can, if we transpose two of the partitions, the Kronecker coefficient stays the same. So first we apply this lemma with this thing, and this thing, and as you can see, I actually transpose two of them, so you can match them above. And then we apply again the lemma. So again, transposing this with adding the blue parts. So we do this twice and we get this identity here. So what are these partitions? These partitions, so they have lambda, mu, and nu here, and you can already recognize them maybe from the theorem. And what we are going to do now, so we already have this identity, but the next thing we need to show is that when we add a very long first row here, this stays the same. And once we do this, we can get rid of these first rows. This is going to be the reduced Kronecker coefficient, and the theorem that I showed would be proved. And so this is the last part, probably the harder part of the proof, is to show that if we add this long first rows to our partitions, which is this H here, though this is what H we are adding, this Kronecker coefficient stays the same. And this is a more general statement, or all we need here is these inequalities, that lambda 1 and mu 1 are long enough. And this always holds. And now we are going to prove this. So, any questions so far? All right. So let me try to prove this, and again, this is gonna be combinatorial. So the first thing I'm going to do, so you will see where this comes from, but let me state this. So we are gonna look at point configurations, which I call 3D binary contingency arrays, meaning that we have a 3D table with entry 0 or 1, which we can also identify as points in three-dimensional space, or these cubes as in the picture. So whenever we have a 1, it means that we have the point, and when it's 0, we don't have that point. And we are going to restrict them to have so-called two-dimensional marginals. So we fix the value of one of the coordinates, the other ones we sum over the all possible other ones. So we have the three marginals that we get. So we sum up how many points, let's say, we have in here, and so on and so forth. And contingency array means that the marginals are restricted. So if we have alpha, beta, and gamma, just some sequences of integers, so basically compositions of the same number, then this C alpha, beta, gamma will be the number of these point configurations, or is the set of all these point configurations, for which the number of points in each plane is given by the alphas, then in the other direction dimension by the betas and the gammas. All right. And now we make the following observation. So if we have marginals alpha, beta, and gamma, so we have some numbers that are bigger than the non-zero parts in alpha, beta, and gamma. And we have that alpha 1 is bigger than or equal to BC plus H, beta 1 is greater than or equal to AC plus H, and the total number of points in this portion, so the top portion, here is less than or equal to H, the number of parts of points, then we need to have a picture like the one that I have drawn here, which means that we have exactly these points in this column. Everything is taken. We have this rectangle, and whatever, something happens in this lower portion. And everything else is zero, so all the other points are missing. And I mean, this is more or less by observation that we see that we have to have this, and in particular we need to have identities, so you can't have too many points in each plane because we are restricted. Because let me see what are the dimensions. So if, let's say, this is B and sorry, this is C and this is B, then what's the maximal number of points we can have in this plane over here is B times C, and if the total number of points above is H, then they would need to be in this plane, they would need to be in the other plane, which means that they have to be in the intersection of the two, and this is restricting the whole picture. So this is more complicated to state than to actually understand what it to see it in the picture, but what we're saying is that we have such point configuration. This is how it should look like. So next, how do we compute Kronecker coefficients using this type of point configurations? And we are going to use this formula. So this is what's called the dual triple Cauchy identity with the Schur functions. So now we have three sets of variables, x, y, and z. We take this guy, so now triple products xi, y, j, z, k. If we expand this in the Schur basis, now this time we get Kronecker coefficients. So if we didn't have the other set of variables, so if it was just x and y, this would be what? RSK. Dual RSK, but this is so one dimension more complicated, and the coefficients we get are Kronecker. Now from this identity, one can prove directly using the Weyl denominator formula that the Kronecker coefficient can be extracted as a monomial from the monomials that we will get as this sign sum over. And what is this? These are the same three-dimensional binary contingency arrays. Where did this come from? Well, it came from this thing. What is this the generating function for? Xi, Yj, Zk. This is the entry corresponding to the point ijk, and if it's 1, then we take this. If the entry is 0, then we take 1. And in the end, we are grouping them by monomial, so we have to have certain marginals that would show up over here. And so there is one step that I did not write down. So this is that we are going to use the Weil denominator formula, determinantal formula, which looks like this. And this is, then we multiply everything by delta x, and this is where all these shifts came from and all these permutations. Okay, so now we want to prove this thing that I mentioned. This is the theorem 2. So using this formula and what? So we are going to use the lemma that I just showed with the point configurations. So what are we counting here? We are counting point configurations Q with these marginals, and what are the marginals are given by whatever is written down here. But let's remember that these are the partitions we are evaluating them at. So lambda 1 in lambda, so actually this is lambda 1 hat here, so lambda 1 hat should be at least whatever L mu 1 plus H minus and plus H, and then sigma 1 minus 1 is a permutation. It has to be at least non-negative. The other marginal as well, you had, and the third marginal. So remember, we are transposing one of the partitions in this picture. So this is, the other marginals are gonna look like this. And there is, so what we can say about the other marginal, so remember, so this gamma prime is going to look like something H, whatever. So these are going to be the values for the values here for the entry that comes from the gamma k prime is going to be equal to 1 for those k's, and then the total sum of points is this thing. These are the maximal possible sum that you can get in this part of the permutation. So this rho k is a permutation from 1 up to c plus h. So this has to be less than or equal to h. And now we have point configuration with these marginal conditions, so then we can say exactly what it looks like, which by the picture back then, it looks like we have everything here, we have everything here in the first side, in the other side, and the rest is happening inside. So this simplifies the whole computation, and what we get is that this Kronecker coefficient, when we are adding the long first row, is equal over the sign sum of this type of binary contingency arrays, which are restricted actually to be exactly this. The only ones where it's this is non-zero. And we can remove basically the H's that show up here, and we get that this is lambda mu nu. So this is one proof. And basically, this is in some sense how we guessed the formula, because we had to use this from the 3D binary contingency arrays. Once you realize what kind of restrictions you are gonna have, you can what kind of restrictions force these configurations, then you can write the identities. So I can show you how the other two proofs look like very briefly. I'm not sure exactly how the time works.
We are very flexible. You can actually just go.
Okay, so if you want to spend another 5 minutes, so another way we can do this, we can use multi-little Richardson coefficients. The formula that I'm showing you comes from using Jacobi-Trudi. Let's say we have S nu x y is equal to our Kronecker coefficients. Like this, and what we can write this Schur function using Jacobi-Trudi as the determinant h nu I plus j minus I x times y, and we know how to expand this guy. So the one row Schur function, or the homogeneous symmetric function evaluated at all the pairwise products, is just equal to all the sums of all products of Schur functions where we have the same partitions here, and of course the partitions need to be of this size. So if we expand this determinant and we group coefficients, and we want to see what is in front of S lambda, well, we're going to be multiplying in the end some kind of Schur functions. And this is why we have this multi-little Richardson coefficient. What's the multi-little Richardson coefficient? It's just that we multiply a bunch of Schur functions indexed by these partitions, and the coefficients are what when we expand this, what we get when we expand this into Schur function. And of course, how do we find these multi-little Richardson coefficients? We can iterate the little Richardson rule over and over. So these guys are still very combinatorial. But of course, what's the problem? The problem is that, well, the Jacobi-Trudi determinant is a signed sum. And yeah, so we get a signed sum of things. Well, for combinatorial interpretation, this is not very useful, but for proving identities, this happens to be useful. So here is what the multi-little Richardson coefficients look like. It's basically a nesting of little Richardson tableau of the corresponding types, so one into the other. So there we have a bunch of types here. These are the different colors, and I put different numbers inside to distinguish. And each of this color tableau should actually be a little Richardson tableau. So ballot sequence, semi-standard Young tableau, and so on. And these are the types. So this is the type alpha 1. alpha 3 and alpha 2 and alpha 3 and so on. Okay, so now we are going to exploit the fact that we have some very special outer shapes for lambda and mu, and we also have some restrictions for the sizes of the alphas. So how is this? Does this work? Of course, for non-zero Littlewood-Richardson tableau, we need to have these partitions. They need to be fit as Young diagrams inside these guys here, right? So these alpha i's belong to both mu hat and lambda hat. And what is lambda hat is, so mu is mu plus h, so the long first row, and lambda hat is gonna be the transpose of lambda plus h. So it's gonna have a long first column. And in particular, we have some restrictions on how these alpha i's are gonna look like. So their length has to be less than or equal to the length of mu, which is, say, b, and the first part is gonna be less than or equal to the length of lambda 1, which is the length of lambda, which is equal to a. And okay, and in particular, so we had some restrictions on the length of the lambdas. So what does lambda look like? So lambda hat looks like something like this. So it has a really long first row. So there is h, and there is b times c or something like that. So this is greater than or equal to b times c. So in particular, when we start drawing our partitions alpha 1, alpha 2, and so on and so forth, the first c of them, so the total height of these partitions for each one of them is at most b. So the first c partitions are not covering more than b times c many boxes from the first column. So there's alpha c comes here, which means that the other partitions that show up in this formula, they need to cover the rest. So this whatever h is sticking out here, and we need to have this inequalities. But what are the sizes of these partitions? Well, remember where we started from. So from this new these constraints, and again, because these are some permutations, this value, the maximum it can have is h, and so h on both sides, we need to have equality here. And what else do we need to have? Well, we need to have equalities everywhere, which means that these alphas are single columns. And now we can argue in a similar way and show that the alphas have to be single rows. And what is it that is single row and single column? It has only one row and one column. It's only this partition. And so we are actually restricted to these partitions that show up here. They have to be just one, and then we can write down the identity basically by removing these parts from this multi-Littlewood-Richardson tableau, because there is no difference in the ends, and the multi-Littlewood-Richardson coefficients would satisfy these identities, and we can just do the algebra, substitute this identity, and in the end we get the same formula, but for the Kronecker coefficients with these parts h removed, so lambda, mu, and u. So this is Another proof, this is not using these point configurations, but some of the arguments are kind of similar. And the last proof, which actually explains also how you can even come up with this formula, comes from the general linear group and has some representation theory. So the Kronecker coefficients are the dimension of the highest weight vector space of weights alpha, beta, and gamma in this wedge product of this tensor product. So here we have three general linear groups, A, B, and C. And what is D? D is going to be the size of our partitions. So where does this formula come from? It comes from Schur-Weil duality, which is giving you some correspondence between the representations of the symmetry group and the general linear group. And this is basically the algebraic version of what I showed in the beginning with this triple Cauchy identity. This is where it comes from, really, from representation theory point of view. And so what are these highest weight vector spaces? These are the vector spaces which are the vectors which are annihilated by the raising operators. And the raising operators are this EI minus 1I. So these are the matrices with only one entry at row I minus 1, column I. Apply to this to our vectors. And the weight of the vector is really given by the sum of the coordinates in each. So these are essentially the marginals that we get. We consider the vectors as some kind of point configurations with coefficients. And so here is an example. We can take. So we live in this tensor space. So we have the basis is given by these three identity vectors, unit vectors EI, EJ, and EK, which we can abbreviate in this way. And so here, for example, is actually a highest weight vector, which is some linear combination of these wedge products. What is the weight of the vector? Think of this as points. So 2, 1, 1, 1, 1, 1, and 1, 1, 2, 2. And again, as thinking of it as point configuration, we need to figure out what the marginals are. And these are exactly 2, 1, 2, 1, and 2, 1. So, and why is it the highest weight vector? Because we can apply these raising operators. So that in this case, there aren't that many, and we can check that it always goes to 0. So this is some interpretation of the Kronecker coefficients. Of course, we don't know how these highest weight vectors in general would look like, but what we can say is that if we are restricting our marginals with our partitions, and if the partitions satisfy the inequalities that were in the theorem, then there is a correspondence between the highest weight vectors for lambda, mu, and gamma, and these guys here. And what is this guy? Lambda plus h, mu hat is mu plus h, and gamma hat is actually gamma and then 1h. And basically then this is the map. And how do we prove this? We use this point configuration lemma again to see that the only possible points take the corresponding shape. And this is so the lemma basically tells us that whatever the highest weight vectors are, if they have such marginals, then they are forced to have points on the first column here in this rectangle, and then everything else is inside, so we can actually get rid of those side points when everything is determined by what's inside. And in particular, there is a correspondence between the highest weight vectors. Okay, so that was it. Sorry for the overtime.
Great. Well, that really brings our seminar to a crescendo. Any questions for Greta?
There is that picture.
This from Mount Whitney.
Ooh.
Where?
Mount Whitney.
Oh, okay. Where is it?
This is the highest peak in the contiguous United States.
And
Sierra
did you
Nevada.
did you take this picture?
Yes.
Oh, you did. Oh, good for you. That's pretty great. Well, if there's no other questions, I'd like to suggest a special round of applause for Anna, who did almost all the work organizing and running the seminar.
Thank you.
Yeah.
I hope you guys enjoy it.
It was
Yeah.
great. Thank you so much. Great talk.
Yeah.
Yeah, great talk, Greta.
Okay, great. Since nobody else is asking, so if you have lambda mu and mu three partitions, and if you just allow yourself to pad each of them with like useless columns, all of the same size, or just adding one to each row, how many different, so to speak, reduced Kronecker coefficients can you get? Like how many degrees of freedom do you actually have? Anyone ever thought of that?
That's an interesting question. I don't think anyone did. I mean, given that people didn't see this identity before anyway. So
Yeah.
So, but it's if you start padding with long enough things, then it becomes trivial. I mean, there's nothing new. But if you're not padding with long enough things, then you have some degrees of freedom.
Well, if the things I pad the different partitions are different, or is it still trivial?
Oh wait, what do you mean?
Oh, okay. No, I meant for the reduced case. Yeah, but it doesn't really make sense because once you pad it to make it unreduced, they become equal again.
Yeah.
Yeah, but on the left, I think you have degrees of freedom.
Yes.
If you padding the first row is maybe too easy, but padding with equal columns might make it more interesting.
And actually, this padding is important to understand. So what happens when you? So it's trivial when you're padding with when somehow the sizes of things you're padding with are related. They're multiples of each other or whatever. But if they are not, then it's not clear what happens.
Oh, right. So if you do your construction many times, of course, it's the same. But yeah, if the sizes are here, then it's not clear.
But so what I didn't say is that the reduced Kronecker coefficients are maybe the simplest cases of other stability phenomena. So there is, like for the Kronecker coefficient, there are, if you add multiples of certain types of partitions, this thing stabilizes. And there were these conjectures by Stembridge, when does this happen, and it was proven by Stephen Sam and Andrew Snowden, that the Kroneckers would stabilize in certain cases when not just when you add long first rows, but you can also add columns, whatever, or some other partitions. So you also have those results.
Mhm.
Okay, well, hope everyone has a great summer. I know classes start here next week already.
Well, mine started yesterday.
Oh, yesterday. Oh, God. All right, back to the salt mine.
Yeah. Thank you so much.
Thank you
Bye.
so much.
Glad you could
Bye,
attend.
everyone.
Thanks everyone. Thanks Anna.
Thank
Thanks, Greta.
you. Bye.